section 7.4, and we are talking about relations and functions. So let's start with understanding these words a little bit. Relation, when we hear the word relation, like you have a relationship, what does that mean? Raise your hand. You have an answer. What does that mean, Brian? You're together. That's exactly right. So relation, if somebody says, sometimes in an old-fashioned kind of book, a novel, they might say, you know, his relations were living in the next village over. And so what are they saying? The relatives, right? So there's some connection there. A relation in math is just a pairing of two things. So it's not one thing. To have a relation, you need more than one thing. So a pairing of numbers. And so it might be an ordered pair, which is a point that could be graphed. So we've been dealing with points, and you've been graphing, and you've done really well with that. One way that we could present a bunch of pairs of data is in a table. So here is a table I put together with a previous class, just kind of thinking about, what do you think the height of people at these ages might be? We know that as you grow up from birth to teenage years, and sometimes even into your 20s, people tend to get taller, right? Sometimes people actually hit their height in 6th grade. And some people don't have a big growth spurt until maybe sophomore year in high school. And then there are people who even grow in college. It's fewer people. Most people do a lot of their growing by the time they're like 16, you know? Girls tend to reach their height before boys on the whole general spectrum, but it varies just person to person, okay? I have one daughter who reached her height in 6th grade, and she was the tallest along with Mrs. Murrah's daughter in 6th grade, and now they're really short people. I mean, they're 5'4". Well, not Michaela maybe, but Haley's 5'4". And then my other daughter just had her growth spurt it started in 8th grade. She was not at her height in 6th grade. And then in high school, she took a little growth spurt too, and then she didn't end up to be too tall either. But anyway, we could imagine that somebody who is 11 could be 48 inches, or another person might be 51. So there's a little bit of variation, but they're kind of in the same neighborhood, huh? A 12-year-old might be 52 inches, another might be 56. Sometimes we have outliers like Michael in 8th grade. I don't know if you remember Colin DeVere back in, he was like 6'5" when he was in 8th grade, so they tend to be what we call outliers. They're like, an outlier is kind of an extreme difference from the average norm, you know. So here we have pairs of data that could be graphed, okay? If we say the age is the input, then we could give it the letter X. Usually in our functions, X's are the inputs, and Y is what comes out after we input something, right? So we call them the outputs. So we could label the ages X's and the Y's the outputs. And there's another name for that. The whole group of number that you input into a function is called something that begins with a D. And I've used this word before. Do you remember? It's the domain. Good. The domain. Okay? So the Y values that come out of the function are not the domain. They are the home on the range. The range. Okay? Imagine a range. A range can be an expansive prairie. I think of a big prairie with like a forest on one end, like Bambi, right? And then river on the other end or something. It's a range, right?
My baby's little skin is Bambi.
Okay, so if we right now, we are identifying right now the domain. What values are in the domain? Give me the values. Audrey.
11.
And?
12.
And?
11.
And?
12.
Okay, so there you go. That's the domain here, the X values. And identify the range. Gabrielle.
48.
And?
52.
And?
51.
And?
56.
Good. So you might just be asked to identify domain and range, and you can do it. Okay? So the domain are the inputs. They are often the independent variable. when we put an equation into function form and we isolate y, we often are allowed to choose whatever numbers we want to plug in. But the range depends on what we plugged in. So if I plug in an 11, I might get a 48, right? The range depends, or is the dependent variable. I'm going to make a quick function that is like something we've done, right? So there is an equation in function form. How do I know it's in function form? It's in slope y-intercept form, but how else do I know that it's in function form, Brian? The y is isolated, good. And so give me some number to plug in. Any number. Is it 5? So we're going to plug that in for x. Do you see how that's independent? She just came up with it. It could have been anything, and she said 5. And now that we plug in 5, what must y be? Say it loud. 16. Once you plug a 5 in there, the partner number must be 16 because that's a function. You see? 16 depended on 5. She chose 5, so we got this dependent 16. Okay? So y depends on what you plug in for x. So a function. A relation is just any pair of numbers at all. We could make any random pair of numbers. But a function is a special kind of relation, okay, where every input has exactly one output. I like to think of it as you can have relationships that are functional or not functional. There's both types. What if I had a relationship that was not functional? What would you think it was like? Colin?
You guys are always arguing.
Okay, so there's something not good about it. Like it's unpredictable, right? I could have a classroom that way too. I could have a classroom that's not functional or a classroom that is. How would that look different? If you walk in my classroom and it's not functional, what would that look like? Hey. Yeah. You would not see what you expect to see. If it's a functional classroom, there's an expectation. You know what's going to be in there. It's going to be stuff going on the way it should, right? You can count on it. That's key. So we have a bunch of relations here. The question is, are any of these relations functions? Or are some of them just random relations? A relation can be a function or it might not be a function. Do you see? So go ahead and take this data down and then we're going to walk through each and see which ones are functions. Okay, so looking at the first relation, again, they're all relations. So looking at this relation, we have all these inputs, right? This is the domain. -1, and the output is 3. 0, 4, 1, 5, 2, 6, 1, 7. 3, 4, 5, 6, 7. Interesting. So is this relation a function? Thumbs up if you think it is. And thumbs down if you think it's not. Okay, so why is it not a function, Alex?
Because the last one, you can't add by 4.
You can't add what by 4?
1 plus 4 doesn't use.
Okay, so we see +1, +1, +1, +1. Doesn't that feel functional? So what do you mean you can't add 4? Oh, you're comparing these two. This +4, +4, +4. He sees that relationship of +4, +4, and this is not +4. That's interesting. Why else is this not a function? Okay. Why should you think this last number should match up with a 3? 1 should match up with a 3? Why are you saying that? Oh, she thinks that this number here, the 1 itself, should be a 3. Who agrees with her there? And that goes along with what Alex was saying. Okay, that's true. And that if it was, you would feel like you had a function, and you would. That's true. And so who else can give me a reason why? What else could we say? Brian?
On the left side, it's +1, but it's equal to it's +1.
Okay, and so another thing is if we look at this, every input has exactly one output. Did we repeat any input?
Yes.
Which input was repeated? One. And so 1 had the output of 5 here. So what should 1 have the output here? Of 5. Right? If it did, could we say this is a function then? Yes, but it's not. So all of those reasons are good ones. You were really thinking well there, logically, about what should be there. And you're right, 3 would have made sense, but not 1. Another way to look at it is if you see the same input twice, it should have the same output. Okay? How about the second one here? We have -1, 0, 1, 2, 1, 2. And then we have 3, 3, 3, 3, 3. It's kind of strange, huh? They all have this output of 3. So is this a function or not? And you can either thumbs up or shake your hand no. Who says it's a function? What do you think? Function? Not a function? And, okay, let's look at it. Most people think it's not a function. Here's an input. It has an output of 3. Does that input repeat anywhere? Another -1? No. Here's an input of 0. It has an output of 3. Here's an input of 1. It has an output of 3. Does that number repeat anywhere?
Yes.
And this input of 1, does it have exactly the same output?
Yes.
Is that a function?
Yes.
Does each input have exactly the same output?
Yes.
Yes, that's what our definition says. Each input has exactly one output. Let's look at this other one. 2 has an output of 3.
Yeah.
Does this input have an output of 3?
Yes.
Is this a function?
Yes.
Yes, it is a function.
What are the 2 top ones?
The 2 top ones are fine. There's nothing to disprove that they aren't a pair, right? If I plug in a -1, what do you think I'm going to get out? If I plug in a 0, what do you think I'll get out? 3. Can we depend on this? Yes. But over here, if I plug in another 1, what will I get out? Will I get out a 5, a 7, a 9, a 6? I don't know. See, this one's not dependable, not a function. Okay, the third one. Now that we've done these, what do you think about the third one? Who thinks it's a function? Who thinks it's not a function? Who thinks it's a function? Who thinks it's not a function? So we have about half a class think it is, and the other half are looking confused. So let's remember the definition. Does every input have exactly one output? So I have -1, 3. Is there another -1 input?
No.
Okay. 0, 4. I have 1, 5. Is there another 1 input, and does it have exactly the same output? So is this a function?
Yes.
Right now, there's nothing to say it's not a function. So we say this is a function. And if this is a function, what do you predict the output is for this too?
6.
Good. We can predict that because there's nothing to prove it's not a function. Okay? Interesting, huh? And now this final table. -1, -1, -1, -1, -1. They're all the same. And then 1, 2, 3, 4, 5. I see a nice pattern. Is this a function?
No.
Yes.
Yes.
No. Yes.
No.
Yes.
No.
And so raise your hand if you think it's a function. We have 3 people. Raise your hand if you think it's not a function. We have 23 people. And you are correct. It's not a function.
Yes.
Okay. So you people who thought it was, you're really logical people. Did you see who raised their hands? They're extremely logical people, and they see the patterns here, and it feels comfortable. If I plug in the next -1 down below here, what do you think will pop out? You think it'll be 6, but how do you know? We really don't, because each time we plug in a -1, something different has come out. It looks like a pattern, but there is not one output for each of these exact same inputs, right? So this is the opposite of this one, which was a function. Isn't that weird?
Yeah.
It depends on the output for each input. They've got to be pairs. And this, look at -1 could be anything, it seems like. Okay, interesting. I'm going to add one more table. And negative 1, 0, 1, 2, 3. And 100, negative 2, 100, 1, 100, 2, 100, 3. Is this a function? And who thinks it is a function? And who thinks it's not a function? It is a function.
How is that a function?
It is because, tell me why it is. I know it looks crazy, the pattern is really strange. Why is it? Ada,
Because there's no identical x's.
there's no same x, right. There's no same x, so there's no way to prove it's not. The only way to prove it's not a function is if I repeated one of these numbers again, like I put in 1, and then if this is a function, what should come out? 101. But if I put, instead I put 104 or something, then it wouldn't be, okay? But at this point, there's nothing to prove it's not. So you do not say it's not a function. Isn't that tricky? Okay, the second way that you could receive the information is just in a group of ordered pairs like this, rather than in a table. So could you take these and put them in a table?
Yes.
Yes, and then you can do the same checking that we've done. Or could you check it without putting it in a table?
Yes.
Do we have any duplicate x's? Do we have any same x value? No. So is this a function?
No.
It must be. There's no way to prove it's not. Okay? So we say function. And here, again, now we have a table. Is this a function?
No,
Tell me why, Lauren. Why is it not?
because you have the same x's, but it's a different value.
So negative 2 gave us a negative 1 output, but this negative 2 gave us a positive 1. So not a function. And then we had problems with this too. But all you need is one problem, like the negative 2's did not give you the same output to prove that it's not a function. Not a function here. Okay? Alex.